All right, so we're going to get started with our talk. Our talk is by Bryan Greer, and Bryan is an engineer and he is a past president of the Columbus Astronomical Society. He has authored several sky and telescope articles on thermal management of telescopes, and he was the editor for H.R. Suter's book, Star Testing Astronomical Telescopes. Bryan is going to talk to us tonight about a 20-year review of Newtonian thermal management. And I just wanted to let everyone know, if you're in the Zoom meeting, feel free to just unmute and ask questions if you have them during the talk. And if you're watching from Facebook, just feel free to ask any questions in the chat at any time. There is a 30-second delay, but someone will moderate your question. I will moderate your question back to the Zoom call so Bryan can hear it. Thank you. And take it away, Bryan.
Thank you, Ness. I just want to see. Yeah, okay. Earlier today when I was with Wilkie, I could see the chat, but anyway, I'll figure it out. Okay, well, thank you very much. And I think, as with most of these things, these are accidental. I mean, I never intended to pursue this. Certainly never intended to do the testing that I did 20 some years ago. But I think it's kind of interesting, and I still, when I think back to it now, I think of the whole story, the whole chain of events that led to my personal revelations about the importance of the thermal equilibrium in the scope, and it's in the 20 years since the articles have come out. I mean, I guess the good news is I think the topic is more. It's more on people's mind now than it was before, but there's also been some misinterpretations, perhaps. I think I know where those came from. A couple of them are partially my fault, which I'll also touch on those at the end, because I think, again, since some time has passed here, it's useful to update things. The actual slideshow, the presentation that I have, it's identical to the one that I gave to the club many years ago. I don't plan on going through that slide by slide. I mean, we'll go through all the slides, but I mean, I'm not going to give the same laborious talk I did before, again, because much of this is now more common knowledge. But there are some useful videos in it and some graphs and things that kind of further the understanding of it. But how this all started was, like many of you, or I know in the club, the CAS has always had a pretty active telescope making subgroup. And many of you maybe have heard the name Bill Herbert. Bill was a past member. He passed away a few years ago, and he generously opened up his basement for I don't know how many years of Saturdays, and allowed us to come in and drink coffee and make mirrors. And it was, at the time, I owned one Newtonian, and I had a refractor, and frankly, I wasn't that interested in Newtonians. I had seen some excellent views through Newtonians, but my interest was planetary. I always, I much more enjoyed the planets and to some degree the moon, but it was mostly the planets that I enjoyed viewing. And the planets are that's the toughest test for an optical instrument. You're at high magnification. The atmospheric seeing, is the most damaging at those high magnifications. And the Newtonians were just messy. Even if you could see the level of detail on them, that, if you had two scopes side by side, a refractor and a Newtonian, you may be able to see just about the same detail in one, but the refractor was just cleaner. You had a darker sky background, and you could just take it right out of the car, set it up, and it worked. So I in the day, I frankly, I made the mirror in Bill's basement just as a interest, I don't know, education, whatever. I'd heard about people making mirrors since high school. I wondered how it worked. So me, along with many other members, we made some very, very fine optics there in Bill's basement. And I set out to make a 6-inch f10, 60-inch focal length, 6-inch telescope, because that 6-inch A was easy to make, but also it matched the biggest APO refractors um, around at the day, and so it would give me something to directly compare to. And it's not that difficult. I'm certainly no master optician. It's not that hard to make a very, very good 6-inch f10. And mine turned out great. Even sent it off to Bill Zemeck and had him interferometrically test it and stuff, and it had good numbers. I put this scope together and took it up to Starfest up in Canada with very high expectations, and it was miserable. It was terrible. It was awful. It was back when you had to pay money, a lot of money, to call the United States from Canada. And I called Steve Keen and probably talked to him for 2 hours, and we were trying to figure out why this scope was so awful. And brought it back to Columbus, and I don't know, maybe a couple of observing sessions right out there in the lawn of Perkins, and the scope again was miserable. And I was just racking my brain what was going on with this thing. And then one night, again at Perkins, a bunch of people were there. Scopes were out. My scope started off the night doing its usual thing, and then went off, had donuts or something, and I'm going to say maybe 2 a.m, sometime really late. Steve and I went back out to the scope. I was about ready to pack it up, and I looked through it, and it was stunning. It was it was like a completely different scope. The detail was there, and you might think, okay, this is atmospheric seeing changing, but earlier in the evening and through all the other sessions, I'm comparing that scope to other scopes of similar aperture, or in some cases identical aperture, and my scope uniquely was performing worse until this one magical moment at 2 a.m. And this completely mystified me. I remember driving home on Route 23 and just thinking, the glass is not changing shape. I'm trying to think what's changing. What are the variables that are changing here? Because I, at the time, like everybody else, I think most everybody else, believed the common wisdom that a small mirror like that, a small telescope, you take it out, give it 30 minutes to acclimate, and you just don't give it a second thought. You just assume it's reached equilibrium. So that was the last thing that crossed my mind. But then I thought back to Bill Herbert's basement sessions, and for those of you who have never made a mirror, the way you test it is something called a Foucault test, which is, I won't go into, but it's a fairly simple test. It's been around for hundreds of years. But the Foucault test is extremely sensitive at showing optical error. That's why they use it. Well, I remembered, after you go and you work on your mirror a little bit and you polish it up, before you can test it, you have to dunk it in a bucket of water and rinse it off. And hopefully that bucket of water is exactly at room temperature, but it never is. And so you take the mirror out and you dry it off and you put it in the test stand. And we commonly had to wait 15, 20, 25 minutes before we could get a really accurate reading on the mirror, because if you tried to look through the little peephole, you saw these little thermal currents rising across the face of the mirror. They show up as these shimmering shadows that go across it. And that's when it kind of dawned on me. It's like, wait a minute, light, the Foucault test doesn't care. The shadows in the Foucault test come from light being deviated from the perfect path. And so if I'm getting the same shadows from these thermal currents as I would if I had a big gouge in the glass, the light doesn't matter. It's being redirected by the same amount. So that's when it started to dawn on me, is it possible this little 1-inch thick 6-inch mirror could be continuing to have thermal problems all through the night? And so that's kind of what started it. And so I was so I don't know, I was so curious about this. I took some time, built a test tunnel, a real long test tunnel, which I think is still stuffed in my dad's storage building somewhere. But I built this test tunnel. I think there's a picture of it in the slides here when I get to them, and basically duplicated the Foucault test in it. And because by that time Bill Herbert had ceased his operations in his basement. And so I did that, and I started to take video of it. And then I thought, I wonder if there's a way to quantify this. The Foucault test, yeah, it's a quantifiable test, but not in the way I needed it to be. I mean, it'll show you the overall shape of the glass, but it's not going to. If you see a little shadow creeping across the mirror, it's not going to tell you that's 10th wave error or anything. But I for some strange reason, when you go to school, some things actually stick in your brain for a while. And I remembered in engineering school, we learned about the Schlieren test. And I think it was literally mentioned one day. I mean, it's not something we labored over. But the Schlieren test is a way that you can quantify if you use a derivative of it called the rainbow Schlieren, which basically what the rainbow Schlieren test does is you put a little color filter. It's like a circular rainbow is what it is. It's like a bullseye target with the rainbow pattern. And if you put that in the Foucault test, now you get a different color for how much error there is. And with some calibration, you can convert that to actual wavefront error. So after doing that, I discovered that, lo and behold, yeah, these optical errors are significant. These are not, 50th wave, 100th wave. Some of these things are one wave, halfway. They're big errors. But the remaining mystery to me was why is it taking this mirror so long to cool? It's a small mirror. If I hook up a temperature probe to it and just set it in my basement, even if I take it out of the hot water, certainly within an hour it reaches room temperature. Well, what I failed to factor in was that, the nighttime temperature continues to fall all night long. We don't observe on cloudy nights. We observe on clear nights when we're radiating heat out to space. And the geography, your own personal geography, turns out to matter quite a bit in this problem. This is why people in Key West, Florida, have never heard of thermal problems, because they have a high temperature of 85 and a low temperature of 75. If you're out in southern Arizona, like Jeff Medkeff was, it goes from 90 to 45, and they have massive thermal problems. And here in the Midwest, we got something in between. So that continuing drop of the temperature gradient, through the night, that's the problem, is that the mirror, even a small 6-inch mirror, can't totally keep up with that. Because the other thing I was curious about was what is the maximum temperature that you can tolerate between the temperature of the surface of the glass and the ambient air around it? In other words, how much does it have to be? How close does it have to be to true equilibrium? And it turns out you got to be about, this is a fuzzy measurement, but you got to be about a degree Celsius, 2 degrees or so Fahrenheit of the same temperature, or you will have visible current. You'll have these little creeping shadows going across your mirror. Now certainly the error is much less at a 2 degree delta T than it is at 10 or 20, but it's still there and it's still noticeable, and you can see it in particular in a star test. If you go up to really high magnification on a star, you can, if you defocus the right way, you can actually see these shadow patterns creeping across your mirror. Or if you have a fan behind your mirror, you'll see a circular cyclonic flow of the thermal boundary layer. But anyway, we'll get to that in a second. So one by one, I started to kind of figure out exactly what this problem was, and I'll say something I said at the beginning. I don't like to oversell this thing. I was a planetary observer, and planetary observing is a tough test. And so these kinds of things are, if you like to observe the planets, this stuff I would, without hesitation, say it's of prime importance. Optical quality is important, things like that, but your thermal management is of prime importance if you're a planetary observer. If you're a casual person going out doing a Messier hunt or something, I'm not going to lose sleep over it if I don't have a fan, or if I got a little bit of thermal problems. It's not that big of a deal. It's just going to make the stars shimmer a little bit or something. So what you're trying to do, what you're trying to observe, also determines how important this is. So anyway, back to once I started to kind of see what the problem was, and then and a little later on, a year or two later, I started to test other mirrors, thicker mirrors, and realized that the thickness, it's the thickness of the mirror. And if you think about it, it makes sense. It's the thickness of the mirror that's the dominant determinant of how readily the telescope will reach equilibrium. It's not the diameter, it's not the total weight, it's the thickness. That's the big one. So if you had like a 6-inch mirror that was 3 inches thick, that would be a nightmare. You know, fortunately, they don't make those. Let me go ahead and fire up the presentation here, because I'll be getting to that in a second. And I got to do a share. Okay, share. For those of you who are, okay, share. Somebody give me a confirmation that you can see something. Okay. Okay, yeah, and you'll notice that we're going back to 2010 here, but hey, some things are timeless. Okay, so with the Schlieren test, with the rainbow Schlieren test, again, the one that allows you to actually put a number to these errors, it was possible to see what conditions must you have in your telescope to where you've really kind of got, you know, put this problem to you know, made it so that it's not going to have a significant degradation to your planetary observing. And like I said, it's about roughly a degree, maybe 1.5 degrees Celsius. It depends on a few other factors too, like when I spent many hours staring at while I was taking video, staring at these patterns going across the mirror, and the things I found out about them was that they're very easily disturbed. In other words, if it's a completely quiescent environment, no airflow at all, you know, this tunnel that I built had walls and stuff around it, then the airflow across this boundary layer, I guess I should define the boundary layer. The boundary layer is this layer. It's a transition layer where you go from where there's a thermal gradient as you go from the ambient, just the surrounding air temperature, to the temperature of the face of the glass. Obviously, that's not a sharp transition. There's a gradual transition there, and that's called the boundary layer. There's all kinds of boundary layers in engineering. There's fluid flow and all kinds of stuff, but this is a thermal boundary layer, and that boundary layer tends to want to be laminar, which means sheet-like. It'll sit there. In fact, sometimes when you look through the tunnel, you don't even see the boundary layer there because it's so laminar. But then my tunnel was 12 feet long, and from 12 feet away, if I just simply exhaled very lightly, just went like that, about 3 or 4 seconds later, poof, I would see that boundary layer unfurl into turbulence. So this boundary layer is very delicate. So this is another thing. This is another variable that, unless you know what to look for and how to track it down, you can be fooled by it, because it'll mislead you, because you may have your scope out one night and there's like 0 wind, and I don't know, you got some other conditions, and you have a laminar flow. And then somebody literally walks by the back of your telescope and kicks that all up, and all of a sudden now you're seeing something different through your scope. You know, again, if you know what you're looking for. So it's, you know, it's one of these subjects that it's good to understand the characteristics of the problem, like, you know, really understand exactly what is going on the face of that mirror. It really does help to have kind of a feel for that. Now, the good news is that what I discovered fixes the problem is super simple, as you can see in the picture here. Hopefully, small, inexpensive fans essentially fix the problem for most of us, and I'll tell you who it does in a second. But for most of us, like certainly my 6-inch f10, I found that a fan on the back, and I did this with carefully attaching, I think maybe I got some pictures of it here, carefully attaching some thermal probes both to the mirror and also an ambient probe and stuff. And I'd go out night after night and track the temperature. Also measure, you can put this on a graph. Excuse me. Let me see if I can advance this slide here. Okay, yeah, I kind of already talked about this. This was my refractor snob days. And this is what I didn't like about Newtonians. And by the way, I'll take a side diversion here. This thing called the usual explanations. Can you see that? Is that showing up?
Yes.
Okay. Yeah. These were some of the common, and still are largely, some of the common complaints that people who prefer I call them refractor snobs, but that's tongue in cheek. I mean, there's legitimate reasons why people prefer refractors, and obviously refractors are probably one of the best instruments to choose for like wide field photography. But anyway, these were some of the common reasons given for why Newtonians were not, as good as people thought they should be. This was some of the testing I did where that top left picture, that was one of the refractors that I owned at the time. And to try to equalize the factors, I actually snapped on a dummy spider, 4-vane spider, onto the refractor so that I could duplicate the diffraction from the spider vanes and the central obstruction. And then on the picture below that's a big light bucket daub, and I cut out an off-axis mask on it, which made the spider invisible. So now it's in theory acting like a refractor. There's no central obstruction, no spider vanes, and that testing still showed that the refractor still bested the Newtonian, even though the Newtonian had no central obstruction, no spider vanes or anything, So this was the early days. This is when I was confused. This is, some of you may remember this. This is Bill's basement making a mirror. So okay, I'm going to skip on up here to where there's the test tunnel. There's my old digital video camera in the end of it. But that's the test tunnel. Okay, now here's a video of the rainbow Schlieren technique. Now this is my hand, obviously, and you can see how there's different colors here. That there's a soldering iron. So a lot of you maybe have seen this video. It's been on a website I've had for a while. So that's what the rainbow Schlieren test does. And this is actually that's the little filter that you put in front of the camera at the right position. So if light is deflected off its intended path, you get the different colors. Brad, I think you were the one that printed those for me, if I'm not mistaken. Yeah, you had the high-tech slide printer, yeah. Okay, so and now here's an actual mirror. This is when there's a little bit of there's a little bit of air movement in the tunnel, so you can see that we do not have laminar flow here. And by the way, I'll get to this too. Laminar flow is not necessarily good. It's just different. But okay, so this is okay. This is as the mirror is cooling down, and you can see the nature of the boundary layer is starting to change. You still have some turbulence across there, but pretty soon here you're going to see the mirror get quite close to equilibrium. Yeah, in this range here, it's probably only a couple of degrees, away from ambient there. Okay, so now a member of the club, Alan Garcia, actually took this video for me, and over a Zoom call, maybe this will be visible, but let's see if I can get that to run again. Oops. What you can see here, if you get a good view of the video, is you should see a bit of a counterclockwise motion. Now, you'll see two things. One is you'll see the conveyor belt of atmospheric seeing. It's too short. Okay, maybe I can stop it. I'll play this for a few times here. Okay, kind of going right to left, you'll see a conveyor belt of atmospheric seeing just sweeping across. That's just, that's a few miles up. But superimposed on that is a counterclockwise general rotation of little turbulent cells or something, and that's right on the face of the mirror. And the reason it's rotating counterclockwise like that is because he had a fan behind it, and the fan will kind of generate some motion like that. But in the important thing to understand here is that if the mirror is in perfect equilibrium, you won't see that. Again, the boundary layer, this is extremely important point. The boundary layer only exists when there is a difference in temperature. So if you can get that temperature of the face of that glass to be essentially the same as the air around it, you're set, you're done. There's no problem. There won't be a boundary layer. So the fact that Alan could capture this on his video tells you that his mirror was not in equilibrium. And that test that you just saw, that video, that's something you can see with a star test. I call it a modified star test because you're not really using it in the traditional way, but basically if you defocus a whole bunch, that's what you can get. Okay, so yeah, I've kind of already talked about this a little bit. The one of the revelations was that this cool down problem, it's not just 30 minutes. Unless you are observing from a location where the nighttime temperature is just not changing, which is not very many places, just to a more or less degree, you will have some issue. Okay, so back to the fan solution. If you just study the problem, I guess as an engineer would, you just look at what variables here would make a mirror, reach equilibrium faster. Well, glass is a very poor conductor, very poor thermal conductor and electrical, but it's very poor thermal conductor. So it gives up its heat very slowly. It stores the heat a long time. So one option, make the mirror out of a different material. Okay, it's just I'm brainstorming here. I make it out of, I don't know, make it out of metal or something. But okay, that turns out to be not a good. The problem is for optical reasons I won't go into. You need something like glass, and pretty much all the materials that optics are made out of are poor thermal conductors. Although pure quartz is about 10-12% better at conductivity. So, okay. Number 2, make the mirror thinner. That one has real promise. And I'll show you some graphs as to why. And then the last one is, of course, accelerate the rate of heat out of the glass, and that's what the fans do. There's only 3 ways that heat is transported. One is convection, where the heat is being carried away by a fluid, in this case the air. That's how the radiator in your car works and your air conditioners work and stuff. So you have a flow of air carrying the heat away. The other one, so that's convection. Then there's conduction, which I think a lot of us are familiar with. If you heat up one end of a spoon, it'll propagate through the spoon and warm up the other end. And then, of course, the last one is radiation, which is how we get all the heat from the sun. There's no atmosphere between us and the sun. That just comes by pure electromagnetic radiation. So these last 2 seem to be some hope. But mainly the fan idea is the one that became the most practical because it's cheap, it's most people can do it, and so forth. After the initial sky and telescope articles, when I start to figure out that the thickness of the mirror was kind of a dominant parameter, I did some more testing, I think a couple of years later, and I had, oh gosh, his name escapes me now. The poor fellow, I think the fellow died. I'm not sure, but he was Robert Royce, Royce optical guy, real nice guy. I used to talk to him on the phone a lot, but I think I heard that he passed away. Somebody correct me if I'm wrong, but anyway, Robert Royce loaned me some blanks, and I had some blanks, and I ordered some quartz blanks, and I got some different materials. I had a man-made ceramic, like a zero door type material, and I started to do a whole bunch of tests. I started to do a whole bunch of tests with both with same diameter but different thickness mirrors. Like this graph here shows 6-inch diameter mirrors. And you can see, the bottom there is minutes. So we're going over 2 hours on the cooling. And now I'm starting out, that vertical axis there, that's not the absolute temperature, that's the temperature difference. So the mirrors started out at, 9 to 10 degrees above the ambient room temperature. And this is an indoor test. So the ambient temperature is not going up or down that much. But as you can see, the thin mirror, it cools significantly. I mean, it reaches equilibrium significantly faster. That was an important thing to understand. And just so you know, for here in Ohio, for our typical temperature gradients after sunset, if you can make a mirror that's about a 1/2 inch to 5/8 of an inch thick, you don't need a fan. You don't need a fan because it's just going to cool itself, and it's going to track. It will track the falling temperature well enough, close enough, just on its own, just through what they call natural convection. A fan is called forced convection, but natural convection is just where the boundary layer just rises due to buoyancy and, just cools itself. So that's kind of the, that would be the sweet point to be at, is if you could get a mirror that thick. Now, obviously, good luck getting a 20-inch diameter mirror made to be 1/2 inch thick. You're not going to get too many opticians that'll want to make that. But for smaller scopes, I've got a telescope here myself that's a 10.6-inch diameter quartz mirror, and it's about I think it's 18 millimeters thick, which is a little more than 5/8. And I haven't had it out yet, but I'm hopeful that scope, it may just work just fine with no fan at all, just because it's thin and it's made out of quartz, which gives off heat a little bit better. So whatever, we'll find out. But okay, but fans. This is a subject that I think I most wanted to address, because I've seen some stories on the news groups, or not news groups, on some of the discussion groups online and stuff, where people they see some of these videos that I posted, of these boundary layers, and they're just like I was, they're horrified by it. And they just like I did, my first thought was, and that I thought, well, I'll just sweep that away. I'm just going to put some fans on there. I'm just going to sweep that boundary layer away. There's a few problems with that. One is several problems. First of all, who wants to take a 2-inch hole saw and cut a big hole in the side of your tube, right in front of your primary mirror? That's one problem. But by far the biggest problem is vibration. The misinterpretation of this, I think, originated from my own videos that showed the boundary layer problem, but also there was another sky and telescope article written by Alan Adler, who was a Stanford professor. And Alan Adler did a really interesting article on what he called a flex mirror. A Newtonian mirror is normally the shape of it, the three-dimensional shape of it is called a paraboloid. It's a parabola spun on its z-axis. And but a paraboloid is a little trickier to make, especially if it's a F5 or F4 or something like that. It's a little trickier to make of high quality. It's much easier to make a perfect spherical surface. That kind of comes naturally. And so his idea was, I'm going to make a thin spherical mirror and then warp it into a paraboloid. Literally flex the glass, because we're to turn a sphere into paraboloid, you're moving the glass a very small amount, but nevertheless. So the way he accomplished this was he glued some foam, neoprene foam, half-inch thick things to the back of the mirror. I mean, literally epoxied it to the back of the mirror, and had a warping harness on there, which he could kind of tighten up with some screws. And he would, I mean, it was a novel idea. He would literally star test the telescope and just keep cranking on this nut until it star tested good, which told him he had a paraboloid. And so it was an interesting telescope. The only problem was, and Gary Saronic at Sky and Telescope put me in touch with him, because Alan was having a dickens of a time with thermal problems with it, as you might imagine, because, well, the back of it's got a half-inch thick neoprene insulator on it. So Alan played around with these frontal fans, these what I call frontal fans, which is the fans that blow across the front of the surface of the mirror. But it's important to remember that he had no choice. The back of the mirror was not available to him. He had to carry that heat away on the front. But the reason his telescope was ultimately not, a total success was because he ran into vibration problems. And Alan's a mechanical engineer at Stanford. He's a professor. He understands these things. He tried, gaskets. He tried this and that. He tried all kinds of things. The problem is that vibration, just due to the way the telescope is constructed, the vibration it very easily transmits up the tube, through the spider veins, and into the secondary mirror, which is hanging out there in space like a tuning fork. And so nowadays with other applications, you'll hear certain little fans being advertised as, vibration free or noise free or whatever, or superior bearings. And I'm sure they are. I don't doubt that. But the problem is none of them are anywhere close to being good enough to suppressing the vibrations that we're talking about. And you can see these vibrations, and you can prove this to yourself, again, through the star test. If the test you want to do is it's most easily done on an artificial star, but you can do this during the daytime. I wouldn't recommend trying to do it at night on a real star, because the seeing conditions don't usually support it. But during the daytime, point your telescope at some very distant, I don't know, something that's got a specular shiny surface on it. People commonly use like those glass insulators on telephone poles or something like that, but just something that's a mile or two away that's got a shiny surface on it. And focus on that at really high power, like about 30 or 40 power per inch of aperture. And then turn the fan on and turn the fan off. And that image should not change at all. And if it does, you have to understand that you're trading one problem, thermal, for what is probably a worse problem, which is the blurring of the Airy disk. The Airy, it's certainly not a perfect analogy, but the Airy disk can kind of be thought of as like the pixel size of a camera or something, in other words, the smallest detail you can see is around the size of the Airy disk. It's the diffraction disk, and it's dependent upon the size of your mirror, your primary mirror. But that Airy disk, when you turn the fan on, that Airy disk cannot be allowed. It just simply can't vibrate at all, because if the Airy disk, swells 50%, you now have the effective resolution of a telescope that's 50% less than, you don't have a 10-inch anymore. You got a 6-7 inch scope in terms of resolution, not light gathering power. So vibration is just not acceptable. You just can't have it. And so when I would see these things online, these people going to a lot of work and, mauling their telescope tubes and all this kind of stuff, and I'm thinking, oh my God, they probably will solve the thermal problem or improve it, but they don't know the other problem they're introducing here, because they're probably not looking for it. Let me let's see here. Okay, there we go. Okay, so what again, Alan Adler in his article, he could not cool from the rear, but obviously most of us do have that surface available, and that's certainly the first one to go to. That's the low-hanging fruit. The only thing I discovered that will completely give you a vibration-free mount is just some sort of an elastic member. These are hair bands that you see in the picture. I've also had success with springs, metal springs. But it needs to be elastically suspended back there. So that's the first thing, is the method that you use to suspend it. The second thing I discovered was, let me see if I got a graph of this, the question I had in my mind is, how much airflow do we need here? I mean, do I need a 6-inch fan back there? Do I honestly did not know. Let me get back to this. Okay. Okay. This first graph just simply shows just how a cooling fan helps you. The green line there is the cooling fan, and that is an outdoor test, I believe. I believe that's an outdoor test. But anyway, so that's on an 8-inch mirror, a little bit bigger mirror. Okay, let me see if I can get. Oh, yeah. This is the graph I'm looking for here. Okay, what this is me testing the cooling rates of a bunch of different blanks of glass with different size fans. But for this graph, I just narrowed it down to the 8-inch mirror, the 8-inch Pyrex mirror, 1.6-inch thickness. So I just wanted that to be a constant. And the red line at the top is no fan at all. So you can see over 2 hours, and you can see how much it dropped there. That purple line, the purple line is the smallest fan. It's that you can maybe see the fan there in the front, the smallest fan. You can see how much benefit you get from that 20 cubic feet per minute, CFM, 20 cubic feet per minute fan. You get that much benefit. If you go up to the 35 cubic feet per minute fan, which is a noticeably larger fan, you do see improvement, but not as much. And then obviously the big 45 CFM fan, don't really see too much difference. And this is exactly what you would expect to see with a material like glass, because what's going on here is that you've got the heat stored in the glass, in the interior of the glass. And the rate of the heat loss is two different things. One is how fast can the heat transport itself from the interior of the glass out to the surface of the glass. And then the second one is the convection. How fast can the airflow carry that heat away? Well, clearly the bottleneck here is not the airflow, because, well, we could put a 400 CFM fan on it. I mean, the airflow is not the bottleneck. It's that heat transport out of the glass that we're sitting around waiting for. So what this shows is that a minimal amount, in fact, quite frankly, even probably something less than a 20 CFM fan would probably have given a lot of benefit here. But for this 8-inch mirror, that little small 20 CFM fan is fine. So that's another way to combat the vibration problem, is don't do what I see a lot of people do. And they just, the fans that you see commonly on computers, at least used to, I think it's a 3 or 4 inch diameter fan for the power supply. That's way too much fan for at least for these smaller Newtonians, 6, 8s, 10s. That's just way too much fan. And the problem is that even if you get a super high quality fan, And every fan blade, the fan blades are injection molded, and so even if you got the perfect injection molded part, every fan blade is exactly the same weight, so that when it spins, you don't get any, out of balance vibration. Even if you have that, there's a reaction force as the fan is churning through the air and propelling the air. There's a differential, there's some unpredictable chaos there. And so in other words, what I'm trying to say is a fan is always going to vibrate. It's always going to vibrate. I don't care what kind of quality it is. So your two best tacks here, don't use too much fan, and to suspend it with an elastic member like that. Now, as a little side note, I do a lot of 3D printing, and one of the things I've been playing around with, and I actually had some success with, if anybody has a 3D printer and they can print TPU, which is polyurethane, some real soft rubbery material, I've come up with some compact damper designs that you can 3D print that do a pretty doggone good job. You can pick up the fan by the edge of the damper and turn it on and off, and you don't feel anything. It's completely dead. It took a bit of trial and error to get that, but that's a little side note. There are, just to show there are maybe some other ways to do this. Okay. Yeah. Okay. Now, another at the beginning of this, one of the caveats I said is that this stuff is most important for planetary observing. There's a few other caveats. First of all, I don't have a lot of direct. I have some experience helping other people out who have large Dobsonian scopes, and giving them some little pointers, or in some cases guesses, and try this, try that. I've never owned a really large Newtonian, and so I don't have a lot of direct experience with what works the best on those, other than what I've had fed back to me. So this last this last comment on the bottom here about avoiding overly complicated strategies, I wholeheartedly still agree with that for the smaller scopes. But when you get into large telescopes, things do change a little bit. Because again, thickness is the dominant factor here. Well, I should say thickness and the rate of the temperature fall at your geography. Those are the dominant factors here. And if you have a mirror that's, let's say, 2 inches, 2.5, 3, even 3 inches thick or something, you will never, unless you live in the Florida Keys, you're never going to be able to reach something really close to thermal equilibrium with just blowing air on the back. It's the thickness is going to keep the front face of that mirror, which after all, that's the one that really matters. It's going to keep the front face of that mirror a little, the delta T, if you will, is going to be a little too high, even with a rear fan. Now, this normally is not the best strategy for solving this is, and that's what I said a few minutes ago about laminar flow is not always necessarily good. If you have several fans around the perimeter of the mirror and you just blow them at the face of the mirror, and your goal here is just to mix it up, churn it up, mix it up. What you do, and this is maybe another talk, but from a Fourier optics perspective, or an MTF, or whatever you want to call it, all this stuff that Dick Suter, another past Columbus Astronomical Society member, Dick Suter, wrote a whole book about this, about Fourier optics, and what types of optical errors cause what kinds of effects that you see with your eye. And if there's a layer of air on the face of your mirror that's distorting the wavefront, and if you then go and just churn it up, mix it up, churn it up, what you do is you what they call the high spatial frequency, which is, in other words, another way of saying the fine detail. The fine detail of the image snaps back. It's preserved. It comes back. You keep the fine detail. The price you pay is you get a little extra light cast all over the whole field of view, which is called veiling glare. Now, if you're doing planetary observing with a 20-inch scope, you're not really too concerned about the veiling glare. The veiling glare, you'll live with that, but you want the fine detail. So just putting fans around the perimeter like that and just mixing it all up, which of course, obviously, is also at the same time helping to carry heat away as well. That's when front blowing fans start to make sense. There's a club up in northern, the Mahoning Club. I forget the name of it. It's about 15, 20 years ago. There's a club up in Northeast Ohio that has it's like a 16-inch Cassegrain or something. It's a catadioptric scope, and but it had a 3 1/4 inch thick mirror, and they spent a lot of money on this thing, built a whole observatory around it, an expensive building and everything, and the telescope just never performed very well, and the cheapy Dobsonians out in the parking lot were outperforming it, and so that's what they did. I went up there and talked to them, looked at it, and they put fans around the outer perimeter, and it helped. Another company that did this was Nikon, and they in Japan they built some fairly large robotic astrographic telescopes, and they had thermal problems in theirs as well, and they just put a ring of little small fans around the perimeter of the mirror just to mix that airflow up, because the veiling glare price that you pay is when you're doing astrophotography, that's a no-brainer, because veiling glare is really easy to process out. When you just have a very slightly lighter sky background, any of you that's processed astrophotos, that's not an issue. You can kind of make that look any way you want. But you want the detail, you cannot fudge that. You can unsharp mask it all you want, but if the detail's not there, it's not there. So when you start getting into larger telescopes, but more specifically thicker mirrors, that's when a scheme of airflow across the front starts to make sense. But again, you are still going to want that. You're going to want those fans suspended with some sort of an elastic member. You don't want to just bolt it to. An interesting side story. I was at Riverside, Riverside Telescope Makers Conference back. It was probably about 2000 or something, and after I did my talk, I was walking around, and this he looked young to me, but this young guy was talking to me, a nice guy and stuff. And he seemed to have a real interest in telescopes and stuff. And I found out he was a freshly hired engineer for Orion telescopes. And this was right before they were coming out with their at the time they were selling those cardboard tube Orion, I forget what they call, Discoveries or something. But anyway, those scopes, but it was before they came out with the Chinese made models, and they were literally in the process of designing those, and he was very curious about the thermal stuff. And I remember telling him several times, just don't bolt the fan to the cell. Please don't bolt the fan to the cell. Well, they bolted the fan to the cell, and I know why they did it, because it's easy. In other words, you got the engineering people at a company, and then you got the marketing people at a company, and the marketing people are saying, well, if we can just tell people we got a fan on there, that most people will buy that. Most people will go for that. So I mean, but there was also some practical elements. How do you sell a telescope to somebody that's got a fan that's mounted by rubber bands or something? But for anybody that has a scope, a commercial scope that's got a rigidly mounted fan to it, I'm not going to say it's useless, because it will, if you turn it on for like 30 minutes before you start to observe, yes, it'll certainly reduce that. It'll bring that mirror down to a lower, a closer temperature faster. It'll do that, but it's certainly not something you would want to use while you're observing. And again, for critical planetary viewing and stuff, you know, with the outside air temperature typically falling, you do want that fan on all the time. You want that fan on throughout the observing session. So just be aware of that. If you've got a commercial scope that's got the fan rigidly mounted to it, you might want to unbolt it and, you know, put some hair bands on it or something. Okay, let me see here. Let me get back to this. And I think I'm getting kind of close to the end of the slides. Okay, yeah, this is kind of unrelated to anything. I just wanted to see what would happen if this was the early days. I wanted to see what happened if you put a little vent door. This is like a side, I don't know if you can tell what this is, but this is a side view of the mirror, and the telescope tube wall kind of inclined up at 40 degrees or something. And you can see that warm air rising off the mirror and kind of crawling up the tube wall like that. And I thought, oh, I'll just put a little escape door there, you know, but another failed attempt. Okay. Yeah. This is some. I think some of these are still believed today. You know, the first one I think is less common now. I mean, you used to hear people say, "Oh yeah, I live in Florida. I don't have thermal problems or whatever." And well, yeah, if you live in the Florida Keys, you're doing fine. But if you live in the Panhandle, no, you got thermal problems. And by the way, in case you wonder why I keep bringing up the Florida Keys, is because they're surrounded by an ocean and little islands like that. You know, small land masses surrounded by a lot of water tend to have pretty stable temperatures. The other one is, you know, again, the common thinking was that people, if you leave your telescope stored in the unheated garage or whatever, then yeah, you never have thermal problems. Well, you'll have less thermal problems. Yeah, I mean, I'm not saying that's, you know, unhelpful, but no, as soon as you take that scope out under a clear sky where the Earth is radiating heat out and the air temperature is dropping, you will eventually develop, you know, some, you know, maybe modest, maybe not so modest, but you're going to develop some disequilibrium there. Again, I've already talked about the front blowing fans. I won't go into that. I think that mostly came from the Alan Adler article and stuff, and people, you know, they saw what Alan did and they some pictures of it, and they thought, oh, that's what I got to do to mine. The other one is that truss tubes telescopes suffer less. Now, I'll tell you where I believe this comes from. As this picture shows right here, when a mirror, and by the way, the mirror in this picture, this mirror was quite warm. I tried to exaggerate the effect. I took that out of a pretty hot bucket of water. But as you can see, when you initially take a telescope out, let's say from room temperature out into a cold winter night, for the first, I don't know, 20, 30 minutes, if it's a closed solid tube telescope, like, you know, your classical telescope, you will absolutely see that warm air hugging the top of the tube wall as it rises out like a chimney and escapes. You'll see that in the star test, defocus, you know, it'll make a mess of things for a while. And people with with truss tubes, they never saw that because there's no tube wall. And so that boundary layer is just, you know, dissipating in the mirror box or something. And so they're not seeing it because that thermal layer is not, that thermal flow is not being confined within the optical path. So that kind of misleads people to think, oh, okay, I got a truss tube, so it's not as big of an issue. But no, this problem the problem you see in this picture, don't worry about this at all. This is a very short-lived condition. Whether you have a fan or no fan or whatever, this is a short-lived. The mirror has to be egregiously warm and out of equilibrium in order to see this kind of an effect. And so obviously, if you have a small fan on the back or whatever, I mean, gosh, within 5-10 minutes, you know, you're not even going to see that anymore. So, okay, so that's the end of that. So
we have a question in the chat from Mark Peter. He asks,
okay, I'm going to bring you guys back so I can see you now. Okay, go ahead, please. Yeah. I think I see how to bring chat up. Yes. Okay, there we go. I guess I got to get the old man glasses. Okay. Yes. Sorry if I missed your comments before. Okay. So that's a Mark. Oh, okay, Mark Peter. Could you use an aquarium air pump instead of a fan? In what way? You mean like have the pump like not not attached to the scope and just have some hoses running to it or something? Is that what you
Yeah,
mean?
that's what I was thinking. You could just attach like a airline tubing maybe to the scope, but have the pump sitting on the ground, not attached.
Yeah, yeah, yeah. Um, I mean, obviously I have not tried it. It would be something interesting to try. The the obvious problem would be you now have got something that's it's going to make the telescope. Depending upon how you do it, I mean, I've given 10 seconds of thought to this, but depending upon how you do it, it could make the telescope more difficult to use. You got to move a stool around or something for the air pump. Um, but and I guess the point I would make, Mark, is that it's usually not necessary for that because the fan solution really does work nice as long as the fan is mounted properly. It's simple, it's quiet, it really doesn't use much battery power. It's part of the telescope, so it's kind of portable with it. Um, it's just when you get up into the big ones. Now, if you do have a large scope, again, I admit I don't have I don't have a lot of tinkering and trial and error with the big scopes, but if you had a big scope where you might want to generate more airflow and maybe have more control over exactly where it goes and stuff, yeah, at that point, yeah, possibly some sort of a kind of a remote pump, might have some benefit. Yeah, I mean, it's a good thought. I will say that one thing I would avoid because I saw somebody, and the guy he appeared to be quite a bit smarter than I am in terms of engineering. Although this particular idea I would not advocate, but it was an Italian guy, probably a PhD, and he really knew how to do stuff. He knew how to program and all this other stuff. But he made thermoelectric a thermoelectric blanket that he put on the back of his mirror. Thermoelectric, if you don't know, you apply voltage to it and it either gets hot or cold, depending upon how you hook it up. And, no moving parts or anything. And the problem with that is that now you've got a feedback loop you got to create. Now you have to have a complicated control system essentially, and that's what he did. He had a complicated control system because although we rarely encounter it, although I have a couple of times, but a cold mirror is just as bad as a warm mirror. I mean, if the mirror is 5 degrees colder than the ambient air, that's just as bad. It's just now the heat flows instead of rising up, the boundary layer is going to be sinking down. So it's just as bad. So the key here is not to quote cool the mirror, it's to get the mirror at the same temperature as the ambient air. So if you put a thermoelectric,
it would actually be worse because you'd get condensation.
Absolutely, yeah. In fact, that's how I knew my that's how I knew my mirror was cold. So anyway, so yeah, so if you try to actively cool it like that, you do have that extra challenge. Now you got to have some some sensors. It gets a lot more complicated. Now again, I'm open minded to anything. If somebody's got a telescope that I'm totally unfamiliar with, a 60-inch diameter, 8-inch thick mirror, whatever. I mean, if they got, who knows? I mean, when you start getting into territories like that, all kinds of technologies, might become more helpful. But for typical amateur scopes like that, the beauty of forced convection, which is fans, is that it can never drive the mirror below ambient. At best, it's going to get it at ambient, which is what you want. So it's kind of, it kind of controls itself.
Brian, how much time are you buying when you shoot the fan at the mirror for a while and then you turn it off? I mean, you would completely solve your vibration.
It depends on where you're at. If you are in Key West, you got the whole night. Shut the fan off. You got the whole. I mean, if it's a 6-inch mirror, 1 inch thick, and if you, let's say you take it out of your hot car, and the mirror is 10 degrees warmer than the surrounding, you turn a fan on for 30 minutes, bring it to equilibrium. Yeah, in Key West, you could probably turn the fan off for the rest of the night because it's just the temperature there just falls so slowly. I've been up till 4 or 5 in the morning before, and it still feels warm, you know. But you know, Jeff Metcalf in Arizona, my gosh, you know, they'd have these blistering hot days, and, you know, and by 2 in the morning, you want to put long pants and a coat on, you know. So that's the general answer. But here in Ohio, the answer is it depends on your thickness. Like on the mirrors I'm most familiar with are 12.5 down to 6. And they range from 1 inch thick up to a little over 2 inches thick. And on the smaller, hang on, we got a vacuum cleaner going now. Oh, hey, sweetie. Thank you. Oh, we got, at least the dogs are not barking. But so anyway, so yeah, like on the smaller mirror, the smaller 6-inch mirror, like if you let's say you start your observing session and everything's in perfect equilibrium and it's a clear night, you know, here in Ohio after sunset, temperature drops 3-4 degrees an hour. You'll probably start to first pick up boundary layer problems maybe after an hour. You know, 45 minutes, an hour, something like that. If it's on one of the bigger mirrors, you would probably know. I don't remember actually observing that, but it probably would be a little bit sooner. So yeah, I mean, like some people have asked, you know, like if they have these commercial scopes where the mirror is bolted, the fan is bolted to the mirror cell or the structure of the scope. And they say, well, can I turn it on for 30 minutes and then turn it off and observe and stuff? And and yes, you can. Yeah, you can do that. But it's kind of like, you know, driving across the country in an electric car. You know, you're going to be taking a lot of breaks, you know. So yeah, but you just, the important thing to understand is that even if you start at equilibrium, it's eventually going to become noticeable if you're doing critical observing of the planets. I was telling Wilkie the story this earlier today, but I can't, well, Steve Keen was there too. He saw it himself. I just, that night on that 6-inch f10 scope that I had, where I had it out many times for, I don't know, 2 or 3 months, and it just was performing miserably. Miserably even compared to my 8-inch f6 that I had from high school, you know, my old clunky scope. But after that thing, I think what must have happened that night at Perkins was that we must have had one of those weird, maybe a front was coming in or something, but I think the temperature just stopped dropping as fast. It was just one of those kind of freaky things, and it allowed the telescope to finally reach equilibrium. And to add to that, maybe some of you who have, you know, spent a lot of time observing with a smaller Newtonian, and you know, and are very familiar with how it behaves. Maybe you've had those nights where it just knocks your socks off. You know, it's like, and now clearly the dominant factor there is atmospheric seeing. That's the one that, you know, kind of takes over. But I'm convinced that those nights when you have that, it's when everything is working, you know, even as little as a slight breeze coming in from the rear of the telescope. See, for 30 years, I never had a fan on my scopes, but I do remember many times being out observing and just feeling a very light breeze. You know, some nights there's no breeze, but sometimes there's a very slight breeze. And as I found out from my fan testing, even a really slight breeze like that, boom, there you go. There's your mirror cooling, you know, front and back, you know. So So anyway, it's for planetary observing. It is one of these things that will make a difference, and oddly enough, it also cleans up the diffraction spikes a little bit too, which I've got some theories on that. But anyway, yes, absolutely. Yeah. Yeah. In fact, that's what Jeff Metcalf was doing that for a while. Yeah, absolutely. Yeah. If you, if you got field power or, got a way to get power to a fan, yes, absolutely. You could blow. And in fact, some of the guys that I've had discussions with over the years with the big Dobbs, that's exactly what they do is they just have a little fan and they just set it behind the scope. And yeah, in some cases that is your best option with the bigger scopes.
I might say something about the aquarium pumps. The amount of air that an aquarium pump moves in 1 minute doesn't even begin to compare with what the tiniest little 1-inch fan can move. Doesn't even,
okay,
not even near it.
Well, my familiarity with aquarium pumps, just watching the little bubbles come out of the tube. So I don't know what they look like a whole lot, but yeah, but
it's just small puffs of air is all it is, and they're forcing it into a tube. And it's usually on 60 cycles per second, and it's going back and forth and just compressing the air is all it's doing. Nowhere near what a fan would.
Well, yeah, and Mark, if I could speak for Mark, I think his general concept is probably more important. The concept of having the compressor remote, not part of the scope.
Right.
So whether it's an aquarium pump or whatever, but yeah, like I said, it's if I had built some big scopes on my own and played around with them more, I'd be able to give you some more concrete, examples of what works and doesn't. But I'm trying to extrapolate what I've learned from the smaller Newtonians. I'm trying to extrapolate that up to the bigger ones and throw in some feedback from people around the world and try to make sense of it. But I'm not going to bet the farm on it.
Yeah. You would probably, even with that, because of the compression, you might even have a fact where it would actually raise the ambient temperature because of the fact that you are compressing the air.
Well, yeah, air's, I think the word is adiabatic. Air very, very, very quickly reaches the ambient temperature as soon as it's like, if you take compressed air and release it out into the environment, it very quickly will. I mean, obviously there's a cooling effect when it expands, but it very, very quickly will, reach the ambient air temperature. So that might not be a problem, but it's just, I like solutions that are obviously as simple as possible and cheap as possible. And, the fans aren't perfect. They've obviously got some hazards to avoid if you're aware of them, but they generally do work. Let me ask, is there anybody, I don't see everybody here, but I know there's some other people here, but has anybody had any interesting experiences with larger like truss tube scopes where they've attempted to actively cool or actively manage the thermal issues? Or, I mean, do they have any success or failure stories or anything? But well, one thing if you're interested, I can loan this to you. I've got a little. It's just a 2-channel thermocouple type, temperature probe thing. It's what I use for a lot of my stuff, but it's just sitting in a box right now. But if you take one of the probes and if you apply it the proper way to the back of the mirror, and the proper way is to put a little thin 1-inch square of foam insulating tape to press it up against the glass, and then I use aluminum tape on top of that just for the mechanical structure. But anyway, if you get that probe on the back of the mirror, and then take the second probe and just it's a real stiff wire, so you can kind of bend it where you want, and just let it stick out 6 inches away from the scope, just to read the ambient temperature. And then night after night after night, you can even record it on a spreadsheet if you want. Just record what that delta T is hour to hour, and you'll get a better feel for what the behavior of that mirror is. And you'll see how steady and consistent it is from night to night, and you'll get a feel for it. And then obviously the obvious benefit is that if you do try some quote fixes, you'll be able to see if your fixes are doing anything or not. But yeah. I have got to get down there. I was telling you on the phone, I keep wanting to take Elliot down there, but he's just so busy now with all of his school stuff and everything, and it's just hard, especially and Fridays and Saturdays are really tough for him. But I'm going to get him down there. Anyway, yeah, I'll talk to you privately about that, because I had a couple questions about that anyway. But we do have a all-wheel drive vehicle, so we could get there in the snow at least.
If nobody else has any more questions, I've been monitored.
I have a question. So
Sure.
I'm curious, and you hit upon it lightly in terms of the advantages of a refractor versus a reflecting Newtonian. And there must still be some thermal impact of the objective
Yes.
in a refractor. So I'm curious, how does that correlate to what you've presented for a reflecting telescope?
Well, let me show you, because in another presentation I have here.
Yeah. I happen to own a very large diameter, fully color corrected objective that
Okay.
is still on the list of projects to be completed.
I've got a graphic. I've got an image that might help. This is actually, okay, yeah. This is actually from, this is from a 21-year-old presentation. So, but it
just dust
let me
it
get you
off.
back, and I'll share this picture here.
This optic is a little over 7 inches in diameter, and I'm assuming, based on some early testing, would be significantly.
Okay, can you see that image?
Yes, I can.
Okay.
I'm sure we all can.
Yeah, you're exactly right. The refractor's got a big, heavy chunk of glass up in the top of it, and that also has thermal issues.
Mm-hmm.
The Newtonian, the reason why the problems are worse is because you can the first of all, the light goes through the thermally messy area twice. On the inbound, and then it reflects on the mirror and goes back out again.
Mm-hmm.
That's the first problem. Second problem is that all that thermal messiness tends to stay confined within the tube, because the thermal mass is at the bottom. Whereas and the metallic coating on the mirror also plays a part in the mirror not cooling as fast. Whereas on a refractor, on the right side there, on the refractor, yes, you've got some thermal messiness there too, but it's on the outside. There will be a boundary layer. There will be a boundary layer on the inside of the refractor's lens, but that's a very laminar sheet-like boundary layer, because the inside of that refractor tube is very stable. It's very quiescent, and you've got the light path is only going through one time. And as you can see, from the blue lines there that show the light path, the vast majority of that light path is going through undisturbed, presumably undisturbed, just clean air. And so and also, again, the refractor, since all that thermal mass is up at the top of the scope, it has a much easier time just getting out of there. And to some degree, depending upon the dew shields you have, the objective lens of the refractor is partially or mostly exposed to the night sky, which means that it can radiate out more heat away as well. So the refractor, I mean, look, anybody that owns a big refractor will tell you that, oh yeah, that they also like to take them out and let them sit for a while, because they do what you'll typically see in a refractor, if it's got some thermal issues, is you will see out around star images, you'll see what appears to be astigmatism. If you do a careful star test, you may see some astigmatism that'll go away after 20 minutes. So refractors do have issues, but they're just not as severe. The Newtonian, just the configuration of it tends to make these problems a little worse.
Got it. No, thank you.
Sure.
Question: in the Newtonian with the full tube there, does the use of a fan contribute, or can you tell much contribute much to excessive dust inside the tube and on the mirror?
The shortest answer is I'm not sure. It's not something I've really done any kind of quantitative testing for, tested A versus B or anything like that. Common sense, I guess, would suggest that, you get more. I'll put it this way: if you've ever taken apart the case of a computer, the box of the computer, the case. Computers obviously have cooling fans and they're flowing a lot of air through them. And if you take the case off of a computer, you'll usually see it's just an absolute dust mess, So yeah, the more air you flow through something, it's going to accumulate more dust. Absolutely. I don't have a good feel for how severe of a problem. In other words, is that going to make you have to clean your mirror twice as often? That hasn't been my experience. I mean, my experience, I use fans all the time now, and I have for 20 years. And I just, I haven't felt any need. And I'm just saying this subjectively. Again, I don't have any direct way of measuring it, but I haven't looked down on my scope and go, oh my God, it's a mess. I got to clean that thing. So I haven't noticed any severe problems with dust and stuff, but I don't know if you're observing on a dry gravel surface or something. If you're observing on something where there might be some dust hanging around low to the ground, then I guess I could certainly see where it might be a problem, but it's just a guess.
Bryan,
I just mentioned it because of the fact. Well, I do work on laser printers and copiers and that. And any time where there's a fan anywhere near, like you say, there is excessive dust, and I was just wondering. And sometimes it's over a 6-month period, it's quite a bit, and these are in clean offices.
Yeah.
Although there is foot traffic, which gets dust to go up.
Yeah.
Just a curious question if you noticed much difference.
Yeah, I have not noticed much. I'm observing from grass locations and stuff, but. I mean, it'd be an interesting thing to get feedback from people on, but I don't know how. I mean, with using commonly available testing tools, I'm not sure how one would really test for that. I mean, as you know, anytime even if you freshly clean a mirror, even if you just got the mirror back from the coater, and if you shine a flashlight down on it, it's going to look all speckled and messy and stuff because it's a brutal test. It shows every imperfection. So I'm not sure exactly how. I think that's one of the problems people. I think that's one of the reasons people might think that that's a problem is they go, oh, I wonder if that fan is causing a problem, and they shine a light down there and they go, oh, it looks terrible. Must be the fan. But yeah, any scope with or without a fan is going to look terrible with a flashlight on it. But I don't know, Jim. I don't know.
I guess you could
just a curious question to bring up. It's just
It's good.
I guess to test it, you could look for loss of contrast or something over time, but generally dust on large optics is just not a problem. because it doesn't
It's
cover
not.
enough of the
It's
mirror.
not. And again, touching on the Fourier optics subject, you know, I was talking before about what turbulence does versus laminar flow, what it does to the image detail. Dust is one of those things that also increases veiling glare. But Dick Souter in his book, he does talk about things like dust and other, you know, small particle imperfections in the optics and what it does to it. He actually models it, and the general conclusion is that a mirror's it's gotta be really, really dirty. I mean, it's you know, I became much less obsessive about cleaning my mirror after reading it. It's toward the end of the book, I think, but he does talk about that a little bit. But yeah, it dust does not take away detail. It in theory at least just adds a tiny bit of veiling glare, just cast light across. So that's not something I'm too terribly concerned about. But
Brian, one thing on a totally different subject, talk about different weather conditions. You know, it's kind of, I always find it ironic that people don't tend to observe on a really hot, humid July night because they're not seeing many stars or planets. You know, like, oh, I can only see one or two magnitudes and the planets, and yet the combination of a steadier sky and the fact that your scope doesn't have to cool very much, you know, you put it out there.
yeah.
I've gotten some of the best images on planets on a hot, humid, terrible quote unquote night in July.
Yeah. No, I absolutely. Yeah, those real muggy nights sometimes. Yeah, as long as you're away from the parking lots and things like that, you know, those can be perfect. Anyway, I don't know how much time, you know, these things normally go.
It goes however long we want it to go.
Until there's nobody left.
Until there's nobody left. At one point, we'll sort of stop the regular meeting, but I actually have a germane question if you're willing to entertain one more.
Yeah.
My intuition doesn't really tell me how all this relates to closed tubes like Schmidt-Cassegrains and that kind of thing. It would seem to me that the you know, tube currents and that type of thing wouldn't be an issue because the air doesn't have anywhere to go.
Yeah. Oh, this is a great question. Yeah. And even though I do own a couple of catadioptric, you know, scopes, a Mac CAS and Schmidt CAS, but first of all, Jeff Medkeff, he's the fellow I keep. He's the late Jeff Medkeff. He passed away also a few years ago. But Jeff got in touch with me specifically because he was testing Schmidt-Cassegrains. One of his friends, David Healy, who retired wealthy from the old Star Wars programs back in the 80s or 90s. But David, super nice guy. He always gave me cheese whenever I was out there. But David Healy had a Meade 16-inch Schmidt-Cassegrain in practically a professional observatory at his house. And it wasn't, and again, he was having problems with it. He wasn't getting, back then they were doing, I think they were doing asteroid hunting with it, and they weren't getting the pinpoint size of the stars that they wanted. So anyway, they on their own stumbled upon thermal as being one of the issues. And so Jeff Medkeff actually spoke at the CAS early 2000s. We flew him out here for that because he shed some light on what he discovered with his Schmidt-Cassegrain testing, and his testing, which started with David Healy, spread to some other local club members who also had Schmidt-Cassegrains. And maybe you've seen that product. I don't know if it's still available or not, but there was a commercially available product for a while called the Limax or something that you could stick up you could stick it up the center of a Schmidt-Cassegrain, and it had a little fan in it. I think it was just made out of like PVC tubing or something, but it would suck air out of the scope. And that was actually, that came from some of that testing with Medkeff. So, but anyway, to answer your question, Brad, this is the conclusion I've come to is you're exactly right. Because remember this, it doesn't matter if the mirror is 200 degrees or 20 degrees. If the air around it is the same, it doesn't matter. So the thing about Schmidt-Cassegrains is that actually the ones that have the more insulating tube materials like carbon fiber, the whole goal, I'm convinced the goal with Schmidt-Cassegrains is just to keep them as bottled up as possible, just to keep them as insulated from the outside air as possible.
Yeah, just get a box of air.
Yeah, and don't get me, this Limax product, there was some good. I mean, in other words, if you use, and this is the way they were using it, is they would stick it into the telescope, for those first 20-30 minutes before they actively observed. They just wanted to kind of get it as close to ambient as they could, but obviously they had to take it out to observe with. But no, once you're actually observing with it, the Schmidt-Cassegrain is such a stable environment in there, as long as you've got it reasonably close to ambient, that you typically don't have to worry about it. Now, maybe you remember our ex CAS member. Gosh, my mind. Who was Brad? Who was the guy from California who was the lighting engineer out in Newark? Mike Packard. Thank you. Yeah. So Mike, you can't remember if you were in Bill's basement this one time, but Mike came into Bill's basement one Saturday. He just bought a C8, C10, something like that. And he says, guys, I think I broke my telescope. Well, what do you mean? He says, oh, I've got a big crack in it now. Well, what do you mean? He says, well, I was out observing, and he said, there's just a big crack going right through the image, And I said, well, I said, even if you had cracked it, I said, I don't think it would look like that, And what it was is that his primary mirror was so warm that the airflow, the flow was rising up off the face of the mirror and then going around that baffle tube. It's got the baffle tube that sticks up through the primary, and it was just like the water going around a rock in a creek. It had to kind of flow around that baffle tube, and this created a very linear structure in the boundary layer, which showed up in his star test. I mean, very conspicuously. It did look like a black line going all across the star test, And but it was just thermal. But once the thing, I mean, that was an example of an egregiously, terribly warm telescope. But a Schmidt-Cassegrain, if it's, as long as you're not taking it out of a super hot car or something like that, it's not going to be affected just because it's so stable inside.
Well, I kind of wonder, one of the issues might be that it's this box of warm air that you have, and you have a large front glass plate, and it's just going to bleed slowly off the buildup heat inside of this large mass of air inside of it, and that's going to never cool down. It's sort of like a refractor on steroids.
Slowly is the key word.
Yeah.
As long as everything is cooling slowly, you're going to be fine, because the mirror, the primary mirror, is really not going to be cooling, or its temperature is not going to be going down as long as the air around it is still the same. So the only thing that's going to make the air around it fall is, like you say, the radiative heat loss out the front corrector. And there is some there, obviously, but it's not, it's a slow heat loss, so that the air within the Schmidt-Cassegrain is also falling slowly, which means that the delta T between the air and the mirror is also small.
So
in other words,
everything's heat is low.
It's like being in Key West. Yeah. Everything is happening slow.
Okay.
The temperature fall is slow. Everything is slow. And now again, this is geography based, because Jeff Medkeff out in southern Arizona, where they have dramatic temperature drops, they were in fact having some pretty severe problems with their Schmidt-Cassegrains because of how quickly things were falling there. So it does depend a little bit, but no, I think the best thing you can do with Schmidt-Cassegrain, in most cases you don't have to do anything, but if you are taking it out from one environment to another where there's a big temperature gain, just flush some air through it with some sort of like I said, this Limax product, if it's still even around, or something. You can make a homebrew type of version, but just circulate some air through there initially, get it cooled the best you can, and then just use it, you know.
Oh, well, okay. So question then, if I, back to the Newtonian problem, if I had a piece of reflective anti-reflective coated glass and put it on the top of the Newtonian, don't I have the same box of air as this other telescope?
You mean
there'll be no airflow inside the Newtonian?
you mean if you had like an optical window in front of it?
Yeah. A piece of glass on the front to close off the air cannot enter or leave the top.
Yeah. I mean, it couldn't just be a piece of glass. It would have to be
optically coated. Yes. But
it would have to be more expensive than your primary mirror, because to make a planar optically flat window of that size is extremely expensive and not easy to do. And so optical windows and Newtonians are a waste of time. What you'd be much better off doing is making a Maxitov Newtonian, which is where the front corrector is the same idea you're talking about, but instead of it being a flat window, you've got two fairly gradual. I mean, you have two. You have a concave and a convex surface, which is actually quite easy to make. It's a Maxitov corrector is very easy to make compared to like a Schmidt-Cassegrain or something. I mean, even amateurs can make them. Because then you not only get the benefit of what you're talking about, which is to close up that volume inside there, but you also correct for coma. You also correct for most of the coma that's inherent in a Newtonian. In other words, you can now use your Newtonian as a wide field imaging device, although you can now do that, of course, with focuser correctors as well. But anyway, but yeah, to your question though, I again, obviously, I have no direct experience with this, but yes, I would think that I would think that if you had a Maxitov Newtonian, I know Astrophysics for a while there made those about 20 years ago, and I'd love to look through one. But if you had a Maxitov Newtonian where the front and the back were sealed up like that, I would expect that to be at least a little more predictable in its thermal behavior. Because one of the crazy things about Newtonians, which I think kind of obscured some of these issues for so many years, was that there's so many variables that, you know, the rate of the falling temperature, is there a breeze, you know, what direction is your telescope pointed, is it catching the breeze, you know, is your body heat getting in the way? I mean, there's so many variables, and not to mention the big one, the seeing, that it's so hard to nail it down and say, oh, you know, this is the problem. So with a sealed up Newtonian with a optical window or Maxitov, whatever, I would think that everything would be a little more stable inside there, so that at least it would be, you know, more predictable from night to night. But you know, you obviously still have the difference that you've got a much larger volume compared to a Schmidt-Cassegrain or something. But no, I don't have any direct experience with that. But it would be interesting to see what the differences are.
Mark Peter asks,
I can scroll down.
And if that has
yes, actually, dew heaters on secondary mounts, as I found out, absolutely create thermal currents. My newest product, actually, the thing, it's completely redesigned, and it uses like 1/3 of the power. There's just here's the answer: is that once dew is allowed to form on a secondary mirror, it takes a lot more power to get that off in a reasonable amount of time. If you want it off in like 10 minutes, it takes a lot more power to get it off once it's formed. It takes a minuscule amount of power to preventatively keep it from forming in the first place. So what I tell people now is I say, look, yeah, you can run this thing at 12 volts all you want. You run it at full power. It's not going to hurt it. But if you want something that has essentially no thermal trace to it at all, just run it at like 4 volts, which happens to be a lithium ion voltage. Just run it at 4 volts, even a AA battery or something. I mean, just run it at reduced voltage preventatively. Just leave it on all the time, and it's going to be such a minuscule. It's like 0.05 watts for some of these mirror sizes. It takes such a small amount to keep the heat, because the reason the secondary mirror dews up to begin with is because it is also radiatively losing heat to the night sky. And so the secondary mirror, over enough time and with the right dew point and other conditions, it will drop, the temperature will drop below ambient to the point where dew forms. So all you're really trying to do is replace that little bit of heat that is lost to the night sky, and that's a real small amount of heat. So yes, dew heaters, absolutely, if they're not used the right way, or if they're just designed with way too much power and so forth, dew heaters, you can definitely see in fact, I've got a video somewhere. I've got a video of, it might be another Allen video, where he had one of my dew heaters turned up full power, and you could see the heat curling off of it, so yeah, you can see it. Oh yeah, hey, the Limax, I remembered it right, limax.com, they still have them. Okay, well, they must work. But,
does anybody else have any questions?
And I'll take a look at that Thingiverse Hyperstar ventilator.
Okay. Well, Bryan, Ness is having internet troubles, so she wasn't able to finish out. But she asked me to relay thank you for coming in. As always,
go ahead.
As always, your talks are very lucid. You take a complicated subject and make it very easy to understand, and the way you explain things is great. So on behalf of Ness and the rest of the club, thank you so much for talking to us.
I realize this is not a topic that, some people don't have an interest in this. They're either not telescope makers, or they're not a planetary observer. It's just not something that, it's not a problem for them. I understand that. But yeah, it is something to be aware of. If nothing else, if you're ever trying to collimate your Newtonian and you just can't get the thing collimated, I'm telling you, sometimes that's thermal. I've been caught in that trap before, where I'll take a hot telescope out of a car and I go to try to collimate it, and I think I got it collimated, and 10 minutes later it's terrible, and I'm going, what is going on? So it'll help you, kind of troubleshoot some other issues, hopefully. So here's another